Okay, so we talk about Fermat's theorem, Euler's theorem. Before that, we talk about Fermat's theorem, Fermat's little theorem, and then the phi function, and then we move to the Euler's theorem in this lecture. So let us just first talk about Fermat little theorem. This is a particular case of Euler's theorem, but this independently invented by the Fermat in Fermat long time back before the Euler's theorem came. So the statement of this theorem is let P be a prime and A be an integer such that A is co-prime to P. That means GCD of A and P are A and P is 1. Then A to the power P minus 1 is congruent to 1 mod P. Okay. So, this is the statement of this Fermat little theorem. It is telling if you take in prime P and if you take a integer A which is co-prime to P, then A to the power P minus 1 is congruent to 1 mod P. Okay. So, how to prove this? So, okay, so proof of this theorem. Okay, P is a prime. So, let us consider ZP. ZP is nothing but 0, 1, 2 up to P minus 1. And if you take the ZP star, the group cyclic group, it is basically ZP minus 0. This is also denoted by R. This is called residue system modulo P class, reduced residue system modulo P. This is the this is called residue set of residue system modulo P, residue system mod P, and this is called reduce the cyclic group where 0 is not there, reduce residue system mod P. This we denote by R. R is basically ZP star, that cyclic group. Okay. So, now if you since P is a prime, then we can show that AR is basically set of all element AR such that R is coming from this. So, AR is basically this set. So, A, 2A, 3A dot 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 like this, P minus 1A. So, these two sets are basically same, AR and R. This we have to prove. Our claim is, this is our claim. Our claim is these two sets are basically same. So, that means number of elements over here is same as number of elements over there. So, this R is basically nothing but 1, 2 up to P minus 1. Okay. So, basically if we take any two element from here, if we can show that they are congruent, then these two sets are basically same. So, how to prove these two sets are same? So, let us try to prove that. Okay, if you take any two element from here, say Na is if we assume they are congruent, M A mod P, suppose. So, N A or M A we are taking from here. So, our claim is that no two elements from this set are congruent. So, these are all distinct elements. So, if these are all distinct elements, then that is basically R. So, to prove that, suppose they are not distinct, suppose there is two element N and M, N A or M A, where N and M are less than p minus 1, less than equal to, are same. Then what we can say? Now, A is co-prime to P. So, A is co-prime to P. So, that means A inverse exists, A inverse mod P exists. So, we will apply A inverse on both sides, is congruent to A, then A inverse mod P. So, this implies N is congruent to M mod P. Okay. So, that means all the elements over here are, so A, 2A, 3A, P minus 1A are basically are congruent to the set 1, 2 up to P minus 1 in some order. So, that means A R is equal to R. So, these two sets are same. Okay. Now, since these two sets are same, so we can multiply the element. So, if you multiply all the elements in A R, so it is basically A into 2A into 3A into P minus 1 into A. So, they are basically, so these are the elements in A R. So, they are basically same as the element in R. So, in a congruent sense under mod P operation. So, that means this set must be congruent to in some order, need not be A is congruent to 1. So, in some order they are congruent to this set 1 to up to P minus 1. So, this will give us what? So, this we can take a common, A to the power P minus 1 into, this is basically 1, 2, 3 up to P minus 1. So, P minus 1 factorial is congruent to P minus 1 factorial mod P. Okay. So, now P is a prime, since P is a prime. So, P has no factor from this 1 to up to P. So, that means P minus 1 factorial, if we denote by say x. So, x is independent, x is co-prime to P. So, from here we can apply. So, this is basically A to the P minus 1 into x is congruent to x mod P. Now, since it is co-prime, this implies x inverse mod P exists. So, we can apply x inverse on both sides. X inverse mod P. So, this will give us basically the Fermat's little theorem, congruent to 1 mod P. Okay. So, this is the proof of the Fermat's little theorem. So, this relationship hold when P is a prime and A is a co-prime to P. A is an any integer which is co-prime to P. Okay. So, this is the Fermat little theorem. So, this was invented long before the Euler's theorem. We will talk about Euler's theorem, which is a generalized form of this, but this was independently invented by Fermat that is why it is called Fermat-Little theorem. Okay, so now we define Euler PhiFunction. Okay. So, it is denoted by so Euler PhiFunction, let n be an integer, we take usually positive integer. Okay. Then we know this set Zn, Zn is basically 0, 1, 2 up to n minus 1, and then we know Zn star. Zn star is basically set of all integer less than n such that positive integer less than n such that such that they are co-prime to n. So, this is the set where we take this is positive integer. So, maybe we can write it properly 0 less than r less than n, r is an integer. So, set of all integer which are relatively prime to n, which are co-prime to n. So, then this set along with this operation can form a group, not for all composite number it will form a group. So, for some composite number it will form a cyclic group. Now, this cardinality of this set is denoted by phi of n, Euler PhiFunction. Okay. So, this is called Euler PhiFunction, cardinality of this set, that means number of element in this set is denoted by Euler PhiFunction. It is the number. So, that means this is denoting by, this is the number of positive integers less than n and which are co-prime to n, less than n and which are co-prime to n. That means those integer whose GCD is basically GCD of r and n are 1. So, that number is called Euler PhiFunction. Okay. So, Euler PhiFunction phi of n is just the number of integer which is less than n, positive integer, and which are co-prime to n. So, that means under Zn, under modulo n, this n has the inverse. Okay. Now we want to know the number of element, I mean we want to know phi n in general, what is phi 7, what is phi 8, what is phi 9 in general. So, if n is a prime number, okay, then we know the phi n. So, for a prime number, Euler PhiFunction is basically, if prime number is p, then it is p minus 1. So, let p be a prime, then phi p is basically p minus 1. Okay. Because if p is a prime, then there is no element which should divide p. So, that means Zn star is basically, so we will not take 0. So, that is r is, so 1 2 up to p minus 1, because p is prime. So, Z p star, p is prime. So, that means all the elements are, so if this is r, all the elements are relatively prime with p, since p is a prime number, otherwise p cannot be a prime number if it is as a factor. So, since p is a prime, this is quite straightforward. then the number of element in here is p minus 1. Okay. Say for example, if p is equal to 7, if p is equal to 7, then we know 7 star is basically 1, 2, 3, 4, 5, 6. So, number of element which is basically 5, 7 is basically 6, which is basically 7 minus 1. Okay. Now, suppose p is not a prime, suppose n is not a prime, suppose n is equal to say 12. Suppose n is equal to 12 and we want to have what is phi 12, we want to know what is phi 12. So, for 12 what is our Zn star, Z12 star. So, Z12 star is basically set of all integer which are less than 12 and which are relatively prime with 12. So, this is basically 1, 5, 7, 11. So, basically phi 12, Eular phi function on 12 is basically cardinality of this set, which is basically 4. Okay. So, we want to have a formula for finding the cardinality of this set, that means phi function in general where n is not a prime. Okay. So, we want to have a formula for this phi function when n is not a prime. So, this will let n is okay. So, this will define. So, let us take another example. Suppose n is equal to 21. So, if n is equal to 21, then that Zn star, Z21 star, which is basically R, reduced residue class. So, that means we are taking all the integer which are co-prime with this 21. So, this is basically 1, 2, 4, 5, 8, 10, 11, 13, 16, 17, 19, 21. Okay. Now, if we take a number a which is co-prime to n. So, that means n is 21. So, if you take a is equal to 5, okay, then we want to define this AR. AR is basically set of all. So, we multiply a with r. So, r is coming from this capital R. So, this set, if we just for this example, it is basically 1 into 5, 2 into 5, 4 into 5, 5 into 5, 8 into 5, 10 into 5, 11 into 5, then 13 into 5, 16 into 5, 17 into 5, 19 into 5, 20 into 5. Okay. Now, this will basically give us 5, 10, 20, 25, 40, 50, 55, then sorry, this is 5, 55, then 65, then 80, 85, 95, 100. Okay. Now, if you perform the modulo operation mod 25, 21, n is 25, 21. So, if you take mod n on this, then it will give us. So, if we apply this mod 21, so it will give us basically 5, 2, 4, 5, 8, 10, 11, 13, 17, 19 and 20. So, this is basically R set. Okay. So, this theorem we have already proved that in general if A is co-prime to n, then AR is basically R. Okay, this theorem we have used in Fermat little theorem, and this we are going to use for the proving the next result on Eular PhiFunction. Okay, so this is by example. This is basically we are getting R back. So, this is by example, but we have already proved this theorem. Okay, so now let us talk about the general form of Euler PhiFunction, where n is where the number is not a prime. So, this is a theorem. So, this theorem is telling let n and m be two integer such that they are relatively prime. That means GCD of n and m are 1. Then phi n into m is basically phi n into phi m. Phi m into n is basically phi m into phi n. Okay. So, this is a theorem, we have to prove this theorem. So, before proving this theorem, let us take an example. Suppose say n is equal to say 3 and n is equal to say m is equal to say 5. Sorry, 5. Okay. So, that means or if we take n is equal to 3 and m is equal to 4. Okay. Then we want to find phi of 3 comma 3 into 4. So, this is basically phi 12. So, phi 12 we have seen it is basically 4. Now, what is phi 3? 3 is a prime. So, phi 3 is basically 3 minus 1, it is 2. Now, what is phi 4? Phi 4 is basically cardinality of Z4 star. So, it is basically 2. So, this is basically 2 into 2, this is basically phi 3 into phi 4. Okay. So, again for say phi 21, how to find phi 21? Phi 21 is basically phi 3 into phi 7. Sorry, this is so this is basically phi 3 into phi 7. So, if this 7 and 3 are relatively prime. So, if you use this result, then we can say this is basically phi 3 into phi 7. So, this is basically this is prime, this is 2 into 6, 12. So, phi 21 is basically 12, and we have seen the phi 21, the elements of phi 21. Okay. So, now we need to prove this theorem in general. So, let us try to prove it. Okay. So, how to prove this theorem? Okay. So, now so let us erase this so we can get more space. Okay. So, we are looking for finding phi m into n, where m n are relatively prime. So, that means we are looking for all number of integer which are less than m into n, m n, and which are relatively prime with n, m into n. So, that means if a is relatively prime with n into m, this implies this is true if and only if a is relatively prime to both n and m. So, both has to be so a is relatively prime to m into n if and only if a is relatively prime with m and a is relatively prime with n, and if this is true, this is vice versa. Okay. So, now we will write these elements 1, 2, we are looking for number of integer over here which are relatively prime with m into n, that means which are relatively prime with both m and n. So, we will write this in a matrix form, this set like this 1, 2, 3, 4 dot 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 n, and then n plus 1, n plus 2, n plus 3, n plus 4 dot 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 2n, 2n plus 1, 2n plus 2, 2n plus 3, 2n plus 4 dot 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 3n, like this. So, dot 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 m minus 1 into n plus 1, then m minus 1 into n plus 2, m minus 1 into n plus 3, then m minus 1 into n plus 4 dot 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 m into n. So, basically we are writing this set in a matrix form, and the okay. So, now we take a j over here. So, this is basically, this column is basically, if we take a j over here, this column is basically n plus j, 2n plus j, like this. Okay. Okay. So, now so this is basically telling us now the first row is basically number of integer co-prime with n is basically phi n in the first row, and this is same as in the second row, because n plus j is congruent to any row, because this is r plus j is congruent to j mod n. Okay. So, that means any row, this is basically phi n is the number of integer which are co-prime to n. Suppose j is the integer, suppose j is co-prime to n. Now, this all are will be co-prime to n, because if j is co-prime to n, then that means GCD of j and n is 1. So, that means n plus j must be co-prime to n, 2n plus j must be co-prime to n, because they are GCD also 1. So, that means all the elements over here are co-prime to n. So, whenever there is a number which is co-prime to n, then that column, all the elements in that column. So, this is a column, jth column, then all the elements in this column will be co-prime to n, and there are phi n numbers. Now we have to see that now we have to see among these how many are basically co-prime to m. So, that we have to see. So, for that so let us take this set. So, this R we take j, this is one column, n plus j, 2n plus j, this is the jth column, where all the elements are co-prime to n. Now, we want to see among these how many are basically co-prime to m. So, there are exactly n element, there are exactly m element in this set. So, that means this is m. Okay. Now, if you take any two element from here, they are in this form R n plus j, and if suppose they are congruent under mod m, we want to see whether this set is eventually z m star or not. This we want to see. Yes, this is z m star. So, that means there are phi n number of elements which are co-prime to m. So, that we want to see under mod operation, mod m operation. So, if they are equal under mod m, so that means R n must be S m under mod m. Now n or m we have taken relatively prime. So, that means n inverse exists under mod m, this exists under mod m. So, if this exists, we can apply n inverse on this. So, this will give us R is congruent to S mod m. So, that means they are congruent to S mod m. So, that means this S, this is basically, this R is basically Z m star. So, that means number of element which are co-prime to m over here is basically phi of m. So, among these, so there are phi n number of elements which are co-prime to n, and among this phi n there are phi m number of elements which are co-prime to m. So, total, so hence the number of elements which are co-prime to both m and n are basically phi n into phi m, and this is basically phi n m, and this is the proof. This is basically phi n m, and this is the proof. Okay, so, just a quick result. So, this we will use to calculate the phi function when n is not a prime, and we need another result. This is also easy to prove. We are not going to prove this. If n is p to the power k, where p is a prime and n is an integer, okay, then phi n is basically p to the power k minus p to the power n minus k. So, this result can be easily proved, but we are not going to prove it now. So, this is also used because if we want to calculate say 9. So, 9 is basically 3 square. So, p is prime. So, we will use this result to prove that. Thank you.